We are all right. We are in section 5.8 now. We've jumped 2 chapters. All right, so hyperbolic functions, they're a family of functions. They're kind of a special class of exponential functions. And the way I understand the kind of the development was this quantity, and we'll talk about it in just a second, showed up so often that people said and they had these relationships that mathematicians said, let's give these functions a special name instead of writing the function out. Kind of like factorial. You in combinatorics, when you're counting things, you end up multiplying a number times every number less than itself. So we said, let's give it a special notation, and we came up with factorial notation. Same kind of idea. Hyperbolic functions, in application, they describe waves in elastic solids. The shape of a hanging cable is approximately a parabola, but because the cable has mass, it is actually described by a hyperbolic function. Temperature distribution in cooling fins is described by hyperbolic functions. So they're a useful family of functions to have some knowledge of, and if you go further into engineering, you'll probably see them a lot. And we'll talk at the very end about why we call them hyperbolic functions, because at first it's not real obvious. So let's do the definitions first. So we're going to define our hyperbolic functions. And once we write our definition, you'll see why we want a shorthand. So we call this, we can call it, I just call it the hyperbolic sine. You can pronounce it sinh. Sinh x is e to the x minus e to the minus x over 2. Cosh x, hyperbolic cosine, e to the x plus e to the minus x over 2. Hyperbolic tangent, or tanh x, is sinh x over cosh x. And then we have our cofunctions. Hyperbolic cosecant of x, or sech. No, sech is secant. Cosech is just like we'd expect, 1 over sinh x, and we're not letting sinh x equal 0. Sech x, hyperbolic secant x, is 1 over cosh x, and cotanh x is 1 over tanh x. And for this one, hyperbolic sine x equals 0 when x equals 0, so we're saying x not equal 0, and here we're saying x not equal 0. So these are our basic functions. We have the hyperbolic sine, hyperbolic cosine. We'll talk about their properties and why we relate them to the sine and the cosine. That's what we're going to do next. And then, again, at the very end, I'll give some motivation as to why we, one, as we go through, we'll see how they're related to the trig functions, and at the end, we'll talk about the hyperbolic part. I'm not going to graph all of these functions. You can find graphs of them in your book on page 384. So on page 384, you'll see graphs of these hyperbolic trig functions. So one reason we relate them to the normal trig functions is they have some identities that are very similar to trig function identities. So let's look at one of those. So let's look at some identities. So let's look at, we're going to look at hyperbolic cosine squared of x minus hyperbolic sine squared of x. And we're going to work through this identity. So from our definition, e to the x minus e to the minus x over 2 squared minus e to the x plus e to the minus x over 2 squared. So when I square this first quantity, what do I get? Did I put them backwards? Yes, I did. Thank you. So what do we get when we square this first quantity? E to the 2x plus e to the negative 2x. And there's one more term. What's our middle term turn out to be? That's this one. So we have, for our middle term, we have an e to the x times e to the minus x. What's e to the x times e to the minus x? E to the 0. 1, and we have 2 of those terms, so we get plus 2. Over 4. E to the x times e to the minus x is e to the 0. We add the exponents, right? Minus, and this will be similar except for a sign. So we get e to the 2x plus e to the minus 2x. And we get a minus 2 there. Over 4. And lo and behold, what happens? Not 0. 1. Because we have a 2 minus a negative 2, and we're dividing by 4. So this equals 1. So cos squared x minus sinh squared x equals 1. So we have this nice identity, very similar to our Pythagorean identity for sine and for our normal sine and cosine. There are other identities that are very, very similar to trig identities, except there are little sign differences here and there. So we could go through, starting from the definition of cosh and sinh, and come up with some other identities. I'm not going to go through the derivations, but we do the same thing, manipulating the definition, and we can find that that tanh squared x plus sec squared x equals 1. And sinh of 2x equals 2 sinh x cos x. You could go through and come up with a whole list of hyperbolic trig identities. You can find others listed, I believe. Did I get the... Others on page, let me make sure I get the page right. I have the page written from the old book. Uh, 384 lists hyperbolic identities. And they all come from starting with the identities, or I'm sorry, starting with the definitions and just manipulating those trig functions. We can also go from the definition and find, because we have these nice exponential functions, we can find the derivatives. So we're in calculus, we want to find derivatives. So if we go starting from the definition, we take the derivative of our definitions and we can come up with the derivatives of our hyperbolic functions. So let's look at a couple of those. So let's look at the derivative d dx of sinh x. So we're going to start with the definition. So we're taking the derivative d dx of e to the x minus e to the minus x over 2. And when I take the derivative of this, what do I get? First I get e to the x plus e to the minus x over 2, which is cosh. Everybody follow that derivative? Pretty easy derivative. And then if we take from our definition, take the derivative of cosh x, we're taking the derivative d dx of e to the x plus e to the minus x over 2. And what happens here? Minus e to the minus x over 2, which is sinh. So similar, except for a sign here. Sign S-I-G-N, not S-I-N-E. And we can go through the other trig functions, starting from the definition, and find our other derivatives. Now for tanh, we can, since we know these already, we can do tanh pretty easily. So we're taking the derivative of sinh over cosh, and now we can use the quotient rule using what we already know. So using the quotient rule on this quotient, what are we going to get? Low d high cosh x times cosh x minus sinh x sinh. Oh, look, doesn't that look nice? Over cosh squared. Cosh x squared minus sinh x squared is 1. And 1 over cosh squared is sec squared x. So kind of a familiar derivative. And we can go through all of these derivatives of all the different hyperbolic trig functions, going through a similar process. So again, what I'm doing today, it's not that I expect us to know everything about hyperbolic functions. Today and tomorrow, I just want you to have seen them. Want you to know a little bit about them. Want you to know that they exist, that there are these relationships. So when you see these quantities, or you see the hyperbolic functions, you'll say, oh, I remember something. But like a student said to me the other day, I asked if that rang any bells, and she said, I think it rings one bell. So hopefully if you see this again, it'll ring one bell. So we did our first three derivatives, and because we have the derivatives, we can talk about the antiderivatives. So what I want to do is, we have the first three, so we'll list the derivatives. I just want to list the derivatives and the antiderivatives of these basic hyperbolic trig functions. So we said that d dx of sinh x is cos x, and that tells us that the integral antiderivative of cos x, dx is sinh x plus c. And we said that the derivative of cos x is sinh x, so that tells us the indefinite integral of sinh x dx is cos x plus c. And we said that the derivative of tanh x was sec squared x. So the antiderivative of sec squared x dx is tanh x plus c. And then the cofunctions are similar. d dx of hyperbolic cotangent is negative cosec squared x. So the integral of cosec squared x dx is negative hyperbolic tangent x plus c. A couple more, and then we're done. d dx of sec x equals negative sec x tanh x. So the indefinite integral of sec x tanh x dx is sec x plus c. And finally, completing our list, d dx, now this is a little tedious, cosec x equals minus cos x hyperbolic cotangent x. So the indefinite integral of this quantity I forgot a negative sign. Negative sign there. What's that? On which last one? Oh, okay. No, that's right. The integral of oh, yes. Yes. Thank you. Okay. Too many C's and S's. Thank you. So those are our basic derivative rules. The homework tonight is basically evaluating hyperbolic functions, hyperbolic trig functions, working with the derivatives, working with the indefinite integrals, just kind of getting some familiarity with these functions. Your calculators might have a hyperbolic trig function menu. I can't remember if the 84s do. We can take a look in just a second. The lesson tomorrow is going to involve the inverse hyperbolic functions, and that's when it gets a little trickier. So it'll be the second part of this section. And there's an interesting article on page 386, a link to an interesting article on page 386 of your book that talks about the hyperbolic functions. Questions on this introduction to hyperbolic functions? So when I first studied hyperbolic trig functions, or in college when I was introduced to them, no one ever explained what do they have to do with hyperbolas. We talk about hyperbolic functions. Why are they hyperbolic? So I wanted to give a little motivation where the hyperbola is in hyperbolic trig functions. So where's the hyperbola? So our regular trig function, sine, cosine, what shape are we talking about? What's our basic shape for our normal trig functions? So if you graph them, you get a wave, a sine curve. But when we think back to when we first started studying trigonometry, what shape were we talking about? Right triangle, and then when we move past right triangle trigonometry, we put the right triangle inside of a circle, and we let the unit radius go around. So we talked about the unit circle, and that was a big thing. So our basic trig functions come from looking at an angle, and that angle describing a point on the unit circle. So we had, I'm just going to do a quick sketch here for our unit circle. I know my circle is not going to be perfect, but we'll get the idea. So if we had some angle here, we were describing a point on the unit circle, and we said that point on the unit circle was, and if we call that angle t, was cosine t, the coordinates were cosine t, sine t on the unit circle. The point on the unit circle is the coordinates are cosine t, sine t. And our basic Pythagorean identity that cosine squared t plus sine squared t equals 1, that tells us that we're on the unit circle. This is x squared plus y squared equals 1. That's the equation of a unit circle, based at center at the origin. So that's where all these identities come from. This is circular, our normal trigonometry. And if we look at the area of this sector, the sector swept out here, the area of the sector is t over 2. Well, if we look back, we came up with one basic identity for the hyperbolic trig functions. We said cos squared t minus sin squared t equals 1. So if I think of this as the x and y coordinates of a point, so I relate this to a point somewhere in the plane, this identity tells me that x squared minus y squared equals 1. That is the equation of a hyperbola. Oh, thank you. So this describes a unit hyperbola. So if we think of this hyperbolic, the t being a hyperbolic angle, and we have a coordinate system over here, x squared minus y squared equals 1 is this hyperbola. And it goes through the point 1, 0. And we're describing some point on the unit circle. And the coordinates of that point are cosh t, sinh t. And the area of this little sector is t over 2. So we can think of the hyperbolic functions as describing a point on the unit hyperbola, and t describing this hyperbolic angle. So that's where the hyperbola comes in, because this basic identity, this relationship, tells us that we're looking at a point on the unit hyperbola. So that's where the hyperbola is. And I never learned that. I had to figure that out on my own. How hyperbolas were related to hyperbolic functions. All right, questions? So our homework, pretty easy. Should be pretty easy. Page 390. There we go.